Hello friends, in this video I am going to solve exercise question from book Topics in Algebra. So question is, are the following mappings automorphisms of their respective groups? First given group is group of integers under the binary operation addition, and given map is T is a map from G to group G such that T of x is equal to minus x. Here we have to check whether this T is an automorphism or not. So firstly we will recall definition of a group automorphism. Therefore we have an automorphism of group G is an isomorphism of group G onto itself. Thus from this definition, to check whether T is an automorphism or not, we need to check that whether T is a homomorphism and also whether T is 1, 1 and onto. So we will do that. Here given group is group of integers under addition and map T is T of x is equal to minus x. Now to check whether T is a homomorphism or not, consider any two elements, say xy in group G, then we have T of x plus y is equal to minus of x plus y. Now this can be written as minus x plus minus y since group G is abelian. Now minus x is T of x and minus y is T of y. So we get T of x plus y is equal to T of x plus T of y, and therefore T is a homomorphism. Next, to check whether T is 1, 1 or not, we will show that, or we will check that whether kernel of the homomorphism T is singleton identity or not. So for that, consider any element, say x in kernel T. Now as x is in kernel T, we have T of x is equal to 0 since 0 is the identity element for given group G. Now this can be written as minus x is equal to 0 since T of x is minus x, and we get x is equal to 0. Since x is any arbitrary element in kernel T, we have kernel T is singleton identity, that is 0, and therefore T is 1, 1 map. Next, to check whether T is onto or not, observe that if y is any element in group G, then there exists an element minus y in G such that T of minus y is equal to minus of minus y, which is y, and thus for any y in G, there exists minus y in G for which T of minus y is y, and therefore T is onto. Thus as T is a homomorphism and also 1, 1 and onto, we can conclude that given map T from group G to group G is an automorphism. Next given group is group of positive reals under multiplication, and map T is such that T of x is equal to x square. So here G is the given group of positive reals under multiplication, and given map T is in this way. Now to check whether T is a homomorphism or not, consider any two elements, say xy in G, then we have T of x multiplied by y is equal to x multiplied by y its square. Now as group G is abelian, x multiplied by y square can be written as x square multiplied by y square. Now x square is T of x and y square is T of y. So we get T of x multiplied by y is equal to T of x multiplied by T of y, and therefore T is a homomorphism. Next, to check whether T is 1, 1 or not, again we will check whether kernel of T is singleton identity or not. So consider any element, say x in kernel T, then we have T of x is equal to 1 since here 1 is the identity element for given group G. Now T of x is x square, so we get x square equal to 1, and thus as x square is 1 and x is any positive real, we have x will be equal to 1, and therefore kernel T will be singleton identity, that is 1, and this implies that T is 1, 1 map. To check T is onto or not, consider any element, say Y in group G, then there exists an element, say X, which is equal to square root of Y in group G, such that T of X, that is T of square root Y, will be equal to square root Y its square, that is Y. And thus, for given element Y in group G, there exists an element X in group G such that T of X is equal to Y, and this implies map T is onto, and therefore as T is homomorphism, which is 1, 1 and onto, we can conclude that map T from group G to group G is an automorphism. Next group is any group G which is cyclic and of order 12, and map T is such that X goes to X cube under T. Now here G is a cyclic group of order 12 and map T is such that X is equal to X cube. Since G is a cyclic group, so G will be generated by some A in group G such that order of A is 12. Then for this A, we have T of A will be equal to A cube. Observe that T of A its power 4 will be A cube its power 4, which is A to the power 12. Now as order of A is 12, so we get A to the power 12 equal to identity, that is T of A its power 4 will be equal to identity, and therefore order of T of A will be a divisor of 4. And if order of T of A will be a divisor of 4, we have order of T of A will be strictly less than 12, which is order of A. Now by this lemma, which says that let G be a group and phi an automorphism of group G, if A is any element of group G with order of A, then order of phi of A will be same as order of A. Now here we can observe that order of A is 12 and order of T of A is strictly less than 12. So by this lemma, we can conclude that map T from group G to group G is not an automorphism. Last, given group G is symmetric group on 3 symbols, that is S3, and given map is T such that under T X goes to X inverse. So this is the given group and this is the given map. Now consider for any two element xy in S3, T of xy will be equal to xy inverse from given definition of a map. Now by Sokshue property, we have xy inverse will be equal to y inverse x inverse. Now y inverse is T of y and x inverse is T of x, so we get T of xy is equal to T of y into T of x, and this shows that T is not a homomorphism. Now as T fails to be an homomorphism, we can conclude that T is not an automorphism from group S3 to itself, and this completes our exercise.